morning everybody. Welcome back once again to our class where we are talking about the halogen and the different halogen compounds. And we are just discussing about the fluorides, how you can utilize the fluorides and how the fluoride compounds are useful for isolation of some industrially important compounds. And we were with the sodium aluminum hexafluoride. So, is a commercial name of it is also Cryolite, where we know that this is the typical isolation procedure for the different cryolite material for the different sources, which can give us the corresponding industrial preparation of aluminum, which is a very important one and is typically an electrolytic process. But if we consider typically as a compound, how sodium aluminum hexafluoride you can get from the typical raw materials, because we were talking about the formation of silicon tetrafluoride and hexafluorosilicic acid. So, earlier we have seen that how hexafluorosilicic acid can be useful for the production of different types of quartz material or the corresponding processing of the quartz material or the glass surfaces. Now, we will see how quickly we can see the reaction if we consider that if you allow to react hexafluorosilicic acid, that means H2SiF6 with ammonia in aqueous medium, that means aqueous ammonia, you are trying to react it with hexafluorosilicic acid. So, what should be your reaction products? In a small scale also, in the laboratory scale, what should be your typical product from that particular reaction? So, one of the important reaction for this particular purpose, one of the pathway for this reaction is that this hexafluorosilicic acid is not very much stable in presence of the water molecule. So, in presence of water, the silicon center, which is under the cover of 6 fluoride ions in an octahedral geometry, will try to go out. That means the silicon fluorine bonds will be broken. If you go down from there, that means from the SiF6 2 minus species to SiF4. There also you have 4 fluoride groups attached to the silicon center, and that is also in presence of your water molecule is not stable. So, what is happening therefore, if some compound is not stable in aqueous medium, in moisture or in presence of water, we see that particular compound can go for hydrolysis reaction. We consider it a hydrolysis reactions. Large number of inorganic molecules or compounds or the organic molecules or compounds are susceptible to this sort of hydrolysis reaction, where that oxygen of the water molecule or the hydroxide group of the water molecule try to attack or hydrolyze the corresponding silicon fluorine bond. So, hydrolysis of that particular one, that means the corresponding SiF4 or H2 SiF6 can undergo for the corresponding hydrolysis reaction. And if we consider that in terms of the anionic ligands or anionic parts surrounding your silicon center, that means in presence of that particular fluoride ions, you can have 6 fluoride groups around the silicon center. So, if all of them or partly 4 of them or 2 of them can be substituted by the hydroxide ions, once water molecule can go for its nucleophilic attack to the silicon center and it can establish new silicon oxygen bonds on the silicon center, and ultimately if that particular hydrolysis reaction giving you silicic acid and at the time passes, it goes to the corresponding formation of silicon dioxide or silica or some amount of quartz we considered in a different form. So, one of them, that means the silicon, the entire silicon what is present in hexafluorosilicic acid will be taken away by water molecules to your silicon dioxide, and the ammonium giving rise to that particular protons of the water molecule giving ammonium ion, and that ammonium ion will be available to trap or to bind your available fluoride groups which are coming out from the hexafluorosilicic acid. So, as a result, in terms of your 6 fluoride groups available on the hexafluorosilicic acid will be taken out by these ammonium ions and ammonium fluoride will be formed. So, 6 molecules of ammonium fluoride will be formed along with your silicon dioxide. So, you get 2 products, one is ammonium fluoride and another is your silicon dioxide. Now, whether this ammonium fluoride can be useful for making your cryolite, that means how we can make synthetically prepared cryolite, because not all the countries are lucky enough or fortunate enough to get this particular natural source of cryolite. But if we can have some other source of aluminum or some aluminum processing industry or the aluminum smelting process or any other sources of aluminum can give rise to a corresponding compound which is easily available as its hydroxide. So, aluminum hydroxide is readily available from different sources of aluminum. It may or may not be your bauxite source, or it may or may not be your typical the scrap aluminum from the aluminum industry. Anywhere you can have the corresponding very low grade or very poor quality aluminum sample, you can convert it by alkali treatment in the basic medium. So, alkaline treatment of that particular one giving you simple aluminum hydroxide. So, now that aluminum hydroxide will be using for the preparation of cryolite. So, your aluminum hydroxide will be the typical source for making your synthetic cryolite, because that cryolite will be, we can use it for aluminum production, the pure quality of aluminum production through electrolysis. So, that particular reaction, that means the ammonium fluoride here is reacting with aluminum hydroxide, and obviously in presence of some excess amount of sodium hydroxide, because that particular reaction between sodium hydroxide and aluminum hydroxide, we know that this can also give you the sodium aluminate formation. So, if we consider that sodium hydroxide and aluminum hydroxide can giving you the sodium aluminate formation, and that sodium aluminate is typically reacting with ammonium fluoride giving you Na3AlF6, which is your cryolite. So, we get the cryolite, we get back the corresponding ammonia which were utilized earlier and the water molecules. So, whatever amount of ammonia we were using, the aqueous ammonia we are using, we are getting back basically from that particular second reaction. So, basically the entire reaction is between the silicic acid and your aluminum hydroxide. So, two components are you are having, one is your corresponding hexafluorosilicic acid and another is aluminum hydroxide, and from that you are making cryolite. So, that can be a very good question for you also when you study this particular course, that you should always remember that if I ask you, or if somebody asks you that how will you get cryolite from aluminum hydroxide, what other thing you require? You require the hexafluorosilicic acid, or how silicic acid or hexafluorosilicic acid is useful for making cryolite in the laboratory or in the industry or in a large scale production. Because this cryolite material is commercially very interesting and is very important also industrially, because it can be used for the manufacture of aluminum. So, aluminum industry is largely dependent on the regular supply of your cryolite material, whether you get it from your natural source or you get it from some other synthetically prepared cryolite. Just now what we have seen, that from the scrap aluminum or any other aluminum, we can make this as your Na3AlF6. Then obviously the second thing, that means the processing of aluminum waste, because the industrial waste or any other thing where we are consuming aluminum. So, this aluminum basically can be your waste material, and that can be processed for very useful cryolite preparation. Sometimes it can also be used as a flux, as we have seen in the terms of a metallurgical component, that this flux, when steel aluminization, that means if we consider that some aluminum is also present in some steel material, because we know the nickel is present, iron is present and the carbon is present from the stainless steel to any other kind of steel, but some aluminum based steel material, we can put this particular material as a flux for steel aluminization and in welding technology, because it can reduce the corresponding fusion temperature for the welding purpose. Then it can be a very good additive for making abrasives. So, abrasive industry is also dependent on cryolites, and in the remelting of light metals, again some kind of material like that of your flux, we can use cryolite to go for the typical melting process, the fusion process, basically what we see, that for melting of gold we know that we use borax, which is a very good flux material. Similarly, for remelting of light metals, not the heavy metals, the light metals, we can use this particular compound, that means cryolite, directly for that particular process. Then we move from alkali fluorides. Just now what we have seen, that ammonium fluoride we can make directly from hexafluorosilicic acid. Now that alkali fluorides are nothing but alkali metal ion fluorides, that means you can have lithium, sodium, potassium and all these alkali metal ions and the fluoride ions as its good salts. So, two of them are very small, that means if we consider that we are talking about the lithium as the lithium fluoride, so it is a very small species, both cation and anions are very small. And as we have seen that in case of aluminum, that hexafluorosilicic acid or AlF6 minus basically is utilizing for your electrolysis. That means for electrochemistry, the other industry which is dependent on electrochemistry can have some good usefulness of these compounds like these fluoride based different alkali metal ions. So, we can have typically lithium fluoride, we can make sodium fluoride, we can have potassium fluoride, but it can be a bisalt with the acid, the free acid, the hydrofluoric acid. That means KF.HF. What is that? It is nothing but your KHF2 bifluoride ion. Instead of typical fluoride ion, sometimes we find that bifluoride ions are much more stable in the solution medium compared to your typical fluoride ion if the protons or the acidic medium is available to you. So, instead of typical calcium fluoride, it can be stabilized further with the addition of the stoichiometric amount of hydrofluoric acid such that you get KHF2, because this HF, one H another F, and you can have the typical electronegativity difference. So, the fluoride center can attract the hydrogen ion end if the hydrogen ion is available. So, the fluoride from both two ends, one side you have one H, another side you have another H, that means FH2 or that is HF2 molecule. So, this HF2 molecule can have to be stabilized in presence of the potassium ion and you get the potassium bifluoride. Similarly, you get the corresponding ammonium bifluoride in your hand also, these are all bisalts. So, the second one, that means sodium fluoride can be utilized further in the manufacture of different organofluorine compound, that you have the organic compound. In our previous classes we have also discussed or seen that you can have in the organic molecule backbone that carbon hydrogen bond, that means CH functions are there, and we can substitute those CH functionality to CF functionality, and that can be achieved very easily through the use of sodium fluoride as the typical inorganic source. So, it gives you the corresponding halogen exchange reactions. What is that? That hydrogen can be substituted, hydrogen atom on the carbon center can be substituted by the fluorine. And as a source of fluorine for toothpaste additives, because as we have seen that apatite is the material, the building material for your teeth, for your bone, etc., and for your teeth enamel. If you can go for the corresponding fluoride derivative, that not instead of hydroxyapatite, you can have the corresponding fluoroapatite, which is much stronger than hydroxyapatite. And that fluoroapatite can be obtained if you go for slow fluorine release or the fluoride ion release rather, is basically through that process of your toothpaste. If you have sodium fluoride, some amount of little bit amount of sodium fluoride in your toothpaste, that slow release of that fluorides while you brush your teeth can be attacked by that of your fluoroapatite formation from the hydroxyapatite on the bone enamel. So, what we use basically sodium monofluorophosphate, because the phosphate is also required for your teeth material. So, instead of directly using sodium fluoride, we cannot use sodium fluoride, but sodium monofluorophosphate, the other end is also phosphate is also getting supplemented. So, these are the material for biomineralization of your teeth. So, alkali fluorides in terms of your sodium monofluorophosphate, because that can also be prepared from your sodium fluoride, can be the corresponding supply for your biomineralization process. Okay. Because all these things, that means the phosphates, the phosphate derivatives, the fluoroderivatives and the fluoroapatite derivatives, they are all mineral like material. So, in situ on the teeth surface, we can make these molecules or this material for your protection of your teeth. Then the potassium bifluoride. So, the other one, that KF.HF or KHF2 is used as a frosting agent in the glass industry. We know that the fluorides will be attacking your silicon dioxide surface of the glass, that means the silicon center can be attacked by your fluoride, but we cannot use directly the hydrofluoric acid for processing or very easy etching process on the glass surface. And sometimes if you require a frosted glass, you require that surface is basically attacked by only potassium bifluoride. So, potassium bifluoride, say simple painting also sometimes can be helpful to give you the frosted glass formation. So, the glass industry is using huge amount of this particular fluorine based compound or this material, and it can be also a very good material for the manufacture of elemental fluorine or the fluorine gas. That means, from KHF2, that fluoride part, we can go for its corresponding oxidation to make the elemental fluorine. Then similarly, the other one, the fourth compound, what we have seen, that we are talking about 1, 2, 3, 4, the fourth compound, which is your ammonium bifluoride. Instead of potassium, because all these cations have some important role to play when it has some application, particularly the industrial application, it has some different role definitely. Instead of the simple presence of ions in presence of the potassium, it is giving some other informations or other reactions which is not able to get it, we are not able to get it through this corresponding ammonium salt. So, ammonium salt is your ammonium bifluoride, and which is useful also for the dissolution of silicate minerals in the extraction of crude oil. So, if we have the crude oil and it has some contamination of the silicate mineral in it, we cannot pass or we cannot allow that silicate mineral to be still there in the crude oil. So, we have to take out that through the attack by your fluoride ions. So, ammonium bifluoride will be the choice for attacking your silicate mineral to remove it as your silicon tetrafluoride. For the pre-treatment of the aluminum prior to anodization and as a frosting agent as like that of your potassium bifluoride, ammonium bifluoride is also helpful for as a frosting agent. And sometimes, since it can also go for attacking your aluminum, the solid aluminum, by the formation of your aluminum trifluoride or the corresponding aluminum hexafluoride, you can go for your corresponding anodization of the corresponding aluminum metallic surface. Then we move to some radioactive material, because we know that uranium processing and all these things we get it from our natural sources. So, uranium oxide, some other material, that the oxides we get. So, the processing of these uranium material, if we are able to get the corresponding formation of its fluoride compound quite easily, we can process that basically for the uranium processing. So, basically this particular compound, that means your UF6, uranium in the hexavalent state, remember it, that is UF6, uranium will be in the hexavalent state, unlike your aluminum or silicon. So, it is basically the most important compound in the separation of uranium isotopes. We get two isotopes, one is 235 and 238. So, you can get the corresponding hexafluorides and we can separate it from their typical properties. That means your physical properties will be different for these two isotopes and we can separate it out. So, if you can have others than this, that means UO2 uranium dioxide, which is a tetravalent compound, that compound or some other uranium oxide source in your hand, which can be directly allowed to react with hydrofluoric acid only, not any other salt. Giving you like silicon tetrafluoride, you again get uranium tetrafluoride and water, and that uranium tetrafluoride can further be oxidized by elemental fluorine to uranium hexafluoride. So, uranium tetrafluoride UF4 is susceptible to oxidation by fluorine. You cannot go for a direct reaction of UO2 with fluorine to get the UF6. You have to go through that UF4. UF4 formation is important, which is nothing but the corresponding addition of the fluoride group to the uranium center, which is in tetravalent state. So, the formation of this is used both in the main uranium enrichment method, that means whether you require for uranium 238, because for the corresponding processing for your nuclear chemistry or reactions, you require some of these isotopes should have the corresponding enrichment, whether you go for uranium 238 for the fission reaction or something for the reactors and all other places, we require the enrichment. So, this particular one, because uranium hexafluoride you are forming here, and if you have the two isotopes uranium 235 and 238, so you will be getting, depending upon the percentage of uranium 235 and uranium 238, you get two of these compounds which are isotopically different. But if you go for a diffusion process, that means the gaseous diffusion and the gas centrifuge method for the separation process, because one will be heavier than the other will be lighter, you can allow for your separation. Then one more important compound what we see from organic chemistry point of view to the industrial sector is nothing but simple boron trifluoride. So, at one end you have uranium hexafluoride, which is the heaviest one. Uranium is corresponding actinides and is the heaviest elements, and the heaviest element also forms fluoride, and the lightest one is your boron in the periodic table. So, periodic table, from boron to uranium, you can think of its reaction with the fluoride ions, you can think of about this oxidation, and you can get some useful compound based on the fluoride industry only. So, how you get this boron trifluoride is again a very simple straight cut reactions, because we are always interested to know the basic inorganic chemistry reactions, because you should know the reaction, how these reactions can be balanced, because on the left hand side most of the time you will find that these are the ores or the minerals. So, the first component for this is your nothing but your Na2B4O7. What is that? Your Na2B4O7 is nothing but your borax, which is again available naturally. So, you can have huge borax source, and that borax, we all know that the borax can be utilized for the formation of boron oxide or the boric acid, which is H3BO3. Now, this is in your hand, and again the fluoride, the calcium fluoride, so that is also a mineral material, so that is also available. Now, you can supply some amount of sulfur trioxide, that we have seen while we are talking about your sulfur chemistry, that sulfur industrial chemistry or the sulfur compounds, we know that how we can get sulfur trioxide. So, sulfur trioxide, calcium fluoride and borax in presence of sulfuric acid. So, is typically a acidic reaction, acidic medium reaction, where we get the boron present in the borax will be reacting with the fluoride available from calcium fluoride to give you the boron trifluoride. So, is basically in some kind of simultaneous double metathesis reaction is happening. So, calcium fluoride is giving you the boron trifluoride basically. So, calcium will take up the sulfate ion from sulfuric acid as well as from sulfur trioxide, because this sulfur trioxide is also available to trap your corresponding oxygen from the borax, and that oxygen will give you for its conversion from sulfur trioxide to again sulfate anion. So, that sulfate anion will be therefore separated as sodium sulfate, because sodium salt of that particular anionic part, that means your B4O7 2 minus is your borax. So, those sodium ions available from the borax will be converted to sodium sulfate, and the remaining as your calcium sulfate, because these two are your byproducts, and these two byproducts, that means your calcium sulfate and sodium sulfate, if we are able to separate them from the boron trifluoride, we can have these two material also as a typical material which can be useful industrially if you can prepare a large amount of calcium sulfate, because we know that is nothing but your plaster of Paris type of thing from the gypsum we get, and your sodium sulfate, which we also prepare from sulfur, elemental sulfur. And this particular thing, that means another indirect way, that if you go for from this particular corresponding your borax, that if you can go for your borax thing, that means borax, if you convert this borax to boric acid instead of direct going for your boron trifluoride. So, if you can have a procedure, or if you can have industry where borax is utilized for making your boric acid, so that boric acid can be your storehouse for that material, and if you require that 50% of that will be used for making your boric acid, and remaining 50% you can go for your boron trifluoride preparation. So, you directly in that particular case you have to react with simple acid base reaction, because if you react it with HF, that H3BO4 can directly react with your that boric acid to give you your BF3 and the water molecule. So, via boric acid also you will be able to make your boron trifluoride. Then from that another boron based compound which is also useful, that boron trifluoride is a Lewis acid. We all know it has 3 fluorine centers on the boron. If you apply another fluoride ion to attach it to this particular center, making it as a BF4 minus ion. So, tetrafluoroboric acid, which can also be prepared from your directly from the boric acid with a different stoichiometric reaction with hydrofluoric acid. Now, you have the 4 molecules of HF reacting with the corresponding one, giving you the free boric acid, because that free boric acid can immediately be converted to its corresponding salt as the sodium salt, which is sodium tetrafluoroborate, because this particular thing is the acid. If you react with sodium hydroxide, then HBF4 reaction of it with corresponding sodium hydroxide or any other sodium salt, it can be a sodium bicarbonate also, to giving you the corresponding NaBF4, which is sodium tetrafluoroborate, which is a very good source of fluoride ion, as well as it is the catalyst sometime, and it also a very good anion, that is BF4 minus, the fluoroborate anion of a different shape, that means a small tetrahedral anionic structure it can have for different types of solid state synthesis or solution synthesis. Then if you substitute this H by alkali metal ion or ammonium ion or any other transition metal ion, you get the corresponding fluoroborates. So, these fluoroborates can be prepared from use of the corresponding acids, and these fluoroborates are utilized as fluxes in the galvanic deposition of metals. So, again from the metallurgical point of view, we now know that what are the different types of fluxes and how these fluxes are also useful. So, if we can go for the deposition of some important metal ions as metals. So, galvanic deposition, that means you have a galvanic cell and you go for a corresponding reduction of the metal ion, and those metal ions are coming out nothing but from your transition metal. If we go for the transition metal deposition, it is transition metal ion fluoroborates. So, transition metal ion fluoroborates in corresponding electrolysis bath, you take it and you can go for its corresponding electrolysis, or sometimes these fluoroborates are also useful as a flame retardant material. So, they can reduce the flame and they can extinguish the flame for some useful purposes. Then we can have the sulfur hexafluoride. So, like your uranium hexafluoride, so now you can get it in terms of your corresponding non-metallic part, that means sulfur you have, and as we have seen that we know sulfur dioxide, sulfur trioxide, but we never discussed it in terms of your sulfur compound, but it is also a important compound based on sulfur, but we are discussing this in the presence of your typical corresponding hexafluoride as the corresponding useful fluoride compound. So, sulfur is taken, but it is basically a useful fluoride compound. So, here SF6. So, SF6 again you can directly use from the elemental reactions between the elemental sulfur and the fluorine, giving you the sulfur hexafluoride compound in your hand. And again, unlike your flame retardant material, but it is a extinguishing agent, it can extinguish the flame. So, flame extinguishing agent in the high voltage power switches, in the transformers and all other cases, because sulfur hexafluoride is basically using that basically utilize that particular gas as a high voltage power switch in different high voltage power switches. It is also a protective gas in high voltage installations in the transformers also due to its high dielectric constant. Based on its typical physical property, having a high dielectric constant value, it can be used, and high electrical breakdown resistance is also very high and is also non-toxic and is also not environmentally so dangerous like other material which we consider that environmentally they are not useful. And it is also useful for inhibiting the ignition of magnesium melts during casting. If we go for a casting material or casting process, and if we go for the inhibition, because magnesium we know that quickly it can burn in presence of oxygen. So, burning of magnesium can be stopped in presence of this sulfur hexafluoride. And in insulating glass, particularly for heat and noise insulation. So, if we can go for insulation of these two quantities, that means heat as well as noise, we can make the corresponding insulating glass made up of silicon hexafluoride. So, silicon hexafluoride will be the raw material for making this special type of insulating glasses. Okay. Thank you very much.